Okay, I replaced yesterday's video with the new one, so it's really clear now because we got a new camera. HD. Except it took like 2 hours to upload it to YouTube. So we reduced it to like a, what am I talking about? We reduced it to something that uses less memory. So hopefully it'll be better.
No, it's got 2 lessons. I don't know why.
Okay, we have questions because the quiz is tomorrow. And you can bet your Bippy the birthday problem is on there.
Oh.
Do you understand the birthday problem? Now today's lesson is quite simple, so if I were you, I would ask a lot of questions. Because yesterday, this class only asked like number 8 yesterday. All the other classes asked like 5 or 6 questions. That's why the video is good, period 6, because they have a lot of questions. The birthday problem? I thought we're experts at it. Apparently not. Okay, 4C. Okay, so we're going to select 3 letters from the word logarithm. Find the probability that at least one is a vowel. Okay, what do you do when you see the phrase at least one? You do the complement. What's the complement of at least one is a vowel? None is a vowel. That means they're all consonants, right? Which is what you did in 4B, right? So you take your answer from 4B and you subtract it from 1. Because it's the complement. That's all you gotta do. You gotta recognize that phrase, at least one means I'm gonna do the complement. And then what? For what? Hanaoka? 4D. You want to do 4D for fun? I heard 4. Everybody can do 4D? Okay.
We do 4D.
Find the probability that 2 are consonants. Okay, let's do a specific case. Consonant on the first draw, consonant on the second draw, and then vowel on the third draw. Okay, so if I randomly select a letter, what's the probability that it's a consonant? 6 out of 9. And then another consonant on the second draw. 5 out of 8. And then a vowel on the third draw. 3 out of 7. However, is this the only way you can get 2 consonants? No, since we're pulling one at a time as an order, you have to multiply by the number of different orders. How many different orders are there here? 3. It's just like how many 3-letter words can you make with 2 C's and a V, right? Or just think about it. The V, the vowel could have been here, here, or there, right? It's 3 cases. I don't care how you count it, you've got to come up with that multiplying factor. Number 5, D, and E. You guys never did like card problems. 3 cards are randomly selected from a deck of 52 cards. Find the probability that D. At least one is, there we go, here's that phrase. At least one is an ace. So when you hear that phrase, what do? The complement. What's the complement of at least one is an ace? None is an ace. And then you subtract it from 1. So not an ace, not an ace, not an ace. What's the probability of pulling out not an ace on the first card? 48 out of 52, right? There's 4 aces in the deck. All the other cards are not aces. What's the probability of pulling out anything but an ace on the second draw? 47 out of 51, and then 46 out of 50. Do I need to multiply that by anything? No, because that's the only way you can get not an ace, not an ace, not an ace, right? How many 3-letter words can you make with that? Just 1, right? And then you subtract it from 1. You do the complements. Now those numbers look kind of ghastly, but I think you guys can handle them. Or maybe not. E, 2 are clubs. So let's do a specific case. Club on the first, club on the second, not a club on the third. Okay, what's the probability of pulling out a club on the first draw? How many clubs are in the deck? 13. Yeah, so 13 out of 52. And then club again. 12 out of 51. And then not a club. 39 out of 50. However, is that the only order you can get 2 clubs? There, multiplied by 3. So it's like how many 3-letter words you can make, right? Or you can think the one that's not a club could have been here, here, or there, right? And for those of you who've been keeping up with your homework, you know that card problems, they simplify nicely, yeah? 13 goes into 54 4 times. 4 goes into 12, 3. 3 goes into 51, 17 times, huh? Card problems always work out pretty nice like that. Okay, and here is the birthday problem. Okay, this problem is on tomorrow's quiz. This is one of the 5 problems. You guys better name it. Okay, now yesterday there were 365 days in a year, so we started with 365 or 365, right? But in this problem, here, let me dumb it down for you then. You're gonna pick 3 people, so just do this. Those are the 3 people. Now we're talking about the days of the week, right? How many days are there in a week?
7.
So what's the probability that the firstborn person is born on the day of the week? 7 out of 7, right? And then 6 out of 7, 5 out of 7. So if you multiply these 3 numbers together, that's the probability that all 3 people have different birthdays. So that's part A. Part B is, what's the probability that at least 2 people are born on the same day of the week? Well, it's the complement of this, so you just subtract it from 1. Nobody better get it wrong tomorrow. I'll take a fipple. Minus 20 just for that one problem. Number 7. A bag contains 4 red marbles. Okay, better. 4 red and 2 black marbles. Bert and Ernie take turns drawing a marble from the bag. The first person to draw a black marble wins. If Ernie goes first, what's the probability that he will win? Now, there are several ways that Ernie could win, right? Couldn't Ernie go first and he just pulls out the black marble right in the first draw?
Yes.
What's the probability of that happening? 2 out of, I'll just write 2 out of 6, you guys can simplify it. Okay, but is there another way Ernie could win? I mean Bert. We're talking about Bert? Or Ernie, but we got black and red though, yeah. Okay, so what's another way Ernie could win? He could go first, but then he pulls out the red marble. Then Bert goes and pulls out a red. And then Ernie goes, and then he pulls out the black on the 3rd draw, right? So what's the probability of this happening? Pulling out a red on the first, a red on the second, and a black on the 3rd. 4 out of 6. Now only got 5 marbles left. 3 out of 5, and then now the black one comes out. 2 out of 4. Is there another way Ernie could win?
Yes.
Yes! He could pull out the red marble, then Bert goes, then Ernie goes, Bert, and then Ernie pulls out the black marble on the 5th draw. So there's another way Ernie can win. So what's the probability of this happening? Red on the 1st, red on the 2nd, red on the 3rd, red on the 4th, and black on the 5th. 4 out of 6, only got 5 marbles left. 3 out of 5, 2 out of 4, 1 out of 3, and then now the black marble comes out. 2 out of 2, which is 1, right? Is there another way Ernie could win?
No.
Are you sure?
Yeah.
How come you can't go red, 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 and then black? Yeah, because there's not that many red marbles in there. So tomorrow, what if I made 6 red marbles? Yeah, I think there would be one more case then. Anyway, what do I do with these 3 numbers here? You add them because there's a big space between them. No, those are mutually exclusive cases, that's what you have. So you write this down on your paper, you get 3 out of 4 tomorrow, and you just gotta compute. But can you see they cancel out kind of pretty nicely? Yeah. Okay, now let me pose another problem to you since we have time today. What would happen if we do the same problem except with replacement.
How do we
You guys know what that means? That means you pull out the marble, you look at it, and throw it back in. What difference is that going to make? Well, what's the probability of pulling out the black marble on the first draw? 2 out of 6. Okay. Let's just write 1/3. No, let's just leave it 2, 6. Okay, what about this one? What's the probability of pulling out a red on the first draw? 4 out of 6. Put it back in, red again. 4 out of 6, and then now the black. 2 out of 6. Maybe we should have reduced it. Let's reduce it for fun. 1/3, 2/3 times 2/3 times 1/3. Okay, what about this case? What's the probability of pulling out a red on the first draw? 2/3, and then a red, and then red, and then red, and then now the black. But then, does it end right there?
No.
No, because there's always going to be enough because you keep putting it back. So then, what's the next one going to be? Red, 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 and then the black comes out. But then, Mr. Park, doesn't this thing just go on forever? Yeah. It does go on forever. So how do we add it up, Mr. Park, if it goes on forever? You use algebra 2. What do you call this? Okay, let's simplify this. Okay, what's the first term? 1/3. Some of you are just dumbfounded, yeah? What's the next one going to be? 4 over 27? And then what's the next one? 8 over 243? And then, come on, Mr. Park, how do you add things up that go on forever? Isn't that impossible? Don't be ridiculous. You took algebra 2. That's an infinite geometric series. What? Okay, let's go back to algebra 2. Let's pretend you never took it. First of all, you guys know what a geometric series is? Okay, when you took algebra 2, remember there are 2 different kinds of sequences. You had arithmetic and geometric. Arithmetic is when you have a common difference. You keep adding the same number every time. Geometric means you keep multiplying by the same number every time. See, look at these numbers. To get from this number to that number, what do I multiply by? What do I have to multiply this by to get that? 4 nines. Is that right?
Yeah.
Except I did something wrong, yeah? This is 16. This is 16. Look, 2 times 2 times 2 times 2. Something's not right here. Anyway, what do I need to multiply this by to get that? 4 nines. So you keep multiplying by 4 nines. So if you keep multiplying by the same number, it's called geometric. And what is the difference between a sequence and a series? Well, this is a sequence. This is what we're learning next chapter, by the way. We're going to spend 1 day reviewing algebra 2, but then we're going to fly after that. This is a sequence. This is a series. What's the difference? This one got commas and this one got plus signs. The definition of a series is it's the sum of the terms of a sequence. That's what a series is. So you're adding the terms of a sequence. And so this is a geometric series, and since it goes on forever, it's called infinite. It's an infinite geometric series. Does that sound familiar from last year? Now, when you have an infinite geometric series here, it looks like this. Okay, this is how it was in your book. Let's call the first term A. And you keep multiplying by the same number every time. We'll call it R. R is for ratio, yeah? If you keep multiplying the next term by R, you get this. This is called an infinite geometric series. Now we learned last year, if the absolute value of R is less than 1, then the sum of an infinite geometric series, I believe that's the way your book wrote it, is equal to the first term over 1 minus R. This is algebra. Every algebra 2 book ever written has that in it. Does that even look familiar? Well, it doesn't matter, right? Because I'm teaching it to you now. So, this is an infinite geometric series. What is the common ratio? What do I have to keep multiplying by? 4 nines. Is the absolute value of that less than 1? Yeah, so that means I can use this formula. So this infinite series is equal to the first term. What's the first term? 1/3 all over 1 minus R. What is the common ratio? 4 9. So this is multiply top and bottom by 9. 3 over 9 minus 4, which is 3/5. So there you go. So you can add an infinite number of numbers up, as long as it's geometric. And the absolute value of the ratio is less than 1. It's just like last year. Okay, this is the problem your teacher showed you last year, I'm pretty sure. 1 plus 1/2 plus 1/4 plus 1/8 plus dot dot dot. If you keep on adding these numbers forever, what are you going to get? Well, first of all, is this a geometric series? Do I keep multiplying by the same number? Yeah, you keep multiplying by 1/2. So the common ratio is 1/2. Is the absolute value less than 1? Yes. So therefore, this is equal to the first term over 1 minus r, which is 2. If I keep on adding these numbers forever, you get 2. Now some of you are thinking, how can you add forever? Yeah, I just showed you how. Now actually, you guys did I'm going to show you since we have time today. Come on, man. Even in, okay, when was the first time in elementary school that you figured out that 0.3 repeating is 1/3? 0.33333 repeating. When did you first figure out that's 1/3? What grade? Third grade? Not preschool? Okay, wherever. You learned it early, right? But this is an infinite geometric series, people. Because isn't 0.3233, okay, what is 0.3? 3/10. And then 0.03 is 3/100. And then this one is 3/1000. And you just keep on adding them up forever, right? So a repeating decimal is an infinite geometric series. What's the common ratio? What do I keep multiplying by to get the next term? 1/10. Is the absolute value of that less than 1? Yes. So therefore, this is equal to the first term over 1 minus r. Multiply top and bottom by 10, and you get 3 over 10 minus 1, which is 3 over 9, which reduces to 1/3. Come on! Is this not ringing a bell?
What happens when absolute value r is greater than 1?
Or not less than 1.
Or not less than 1.
Then the series, we say, diverges. In other words, it doesn't add up to a finite number. For example, like this. What if you had this? 1 plus 2 plus 4 plus 8 plus dot dot dot. Is that a geometric series? What number do I keep multiplying by? Okay, we keep multiplying by 2. Now a lot of people, they don't know anything. All they know is, I saw this formula in the book. So this is equal to the first term, all over 1 minus r. What's the common ratio? 2, so it's -1. If I keep on adding these numbers forever, you get -1. Can you see that's dumb? How can you add up all, and the numbers keep getting bigger, you can get -1 as your answer? No, that is why you can only use this formula when the absolute value of r is less than 1. Otherwise, as we say, the series diverges. That's why this one actually diverges to infinity. You get the infinite sum, yeah.
Is that formula in next chapter's notes? Or do we have to
No,
do
2 more chapters. See, the next chapter we're doing sequences with the commas.
Oh,
Then the chapter after that, then we add them up.
also, we don't have to write that down yet. Or like,
I'm telling you what happens if you did this problem with replacement. What if you replace the marbles every time?
also you should write it down then.
Okay, see, we figured it out. Okay, now tonight's homework is, we're going to do the exact same problems as last night's homework, except we're going to do it a different way. So that means there's 2 ways of doing it, and I don't care which way you do it. Okay, let me try to think of the example I did yesterday. You have a bag. It contains 4 blue, 3 red, and 2 green marbles. I am going to randomly select 3. Okay, and again, if I don't say anything, you assume without replacement, right? What is the probability of getting 1 of each color? Didn't we do this problem yesterday? You were here 24 hours ago, right? Oh my goodness. Okay, so this is the way we did it for last night's homework. Okay, do a specific case. Get a blue on the first, a red on the second, and a green on the third. What's the probability of that happening? Blue on the first. 4 nines. Only got 8 marbles left. What's the probability of getting a red? 3/8. Only got 7 now. 2 7s. But how many different orders can you put them in? Because when you pull out marbles one at a time, there's an order, first, second, third, right? Is that the only way you can get one of each color? No, you could have got green first, then red, then blue. What about red, then blue, then green? So how many different orders are there? 6, so you have to multiply by 6. When you pull out the marbles one at a time, it's a permutation. There's an order, so you have to multiply by the number of different orders. Now what we're going to do in tonight's homework is, instead of pulling out the marbles one at a time, what happens if you just grab all 3 at once? You put your hand in the jar and you pull out 3 marbles. You don't pull them out one at a time, all 3 at once. Now if you do that, then that's not a permutation anymore, it's a combination, right? You're just picking out 3 marbles, like making a committee. Okay, so how would you do the problem? Well, what's the denominator going to be? How many total marbles are there in the jar? There are 9 marbles. How many ways can you pick 3 of them? 9, choose 3, right? That's the denominator. Now, we want 1 of each color. Well, how many blue marbles are in the thing? 4. How many ways can I pick 1 of them? There's 3 reds. How many ways can I pick 1 of them? And there's 2 greens. 2, choose 1. Boom, that's your answer. You don't need to multiply by anything because there is no order, because you pulled out all 3 marbles at once. You get it? This one, you pulled out 1 marble at a time, that's why you have to multiply it by the number of orders. But if you pull out all 3 balls at once, there is no order. That's your answer right there. And just to show you, look, let's compute this. If you have to compute this, 4 times 3 times 2. And then what is 9 choose 3? What's the shortcut for that? 987. 987 over 3, 2, 1. But when you divide by a fraction, that's like multiplying by the reciprocal. So this 3, 2, 1 actually goes up here, right? Can you see that that's exactly the same as this? Look, 4 9s, 3 8s, 2 7s times 6. It's exactly the same. And it should be. It's just a different way of thinking about it. Okay, let's do one more example. One more example should be sufficient. Okay, randomly select 3. What's the problem? I'm trying to remember what we did yesterday. Was it 2 red and 1 green?
Yes.
Okay, 2 red and 1 green. Okay, this is the way we did it yesterday. Do a specific case. Pull out a red on the first, a red on the second, and a green on the third. What's the probability of that happening? 3 9s, and then another red, 2 8s, and then now the green. 2 7s. But how many different orders can you get 2 reds and a green? There's 3 orders, so you gotta multiply by 3, right? Okay, but now let's do it using combinations. So the denominator is gonna be 9 choose 3, right? We're just gonna pull out all 3 marbles at once. Now what about the numerator? We want 2 red and 1 green. How many red marbles are there? How many ways can I pick 2 of them? 3 choose 2. And how many green marbles are there? 2, and I want 1, so 2 choose 1. Boom, that's the answer. You do not multiply by anything because there is no order. Okay, let's compute this. 3 choose 2 is 3 choose 1, which is 3. 2 choose 1 is 2. 9 choose 3 is 9, 8, 7 over 3, 2, 1, but then the 3, 2, 1 comes back up here. Can you see that that's exactly the same as this? Look, 3 9s. 2 8s, 3 7s, and then 3. How come this? Oh yeah, 2 7s. 2 7s and then 3. It's exactly the same. Now, on the test, by the time we take the test next week, I don't care which way you do it. You can do it either way. Which way looks better right now? The permutation way or the combination way? Now, combination way is probably easier to understand, but if you're in a math contest, I think this way is faster. You know why? Because once you write it down, you can let the canceling begin already, right? But over here, you write this down, and then you gotta write this before you can let the canceling begin. You know what I'm talking about? But I don't think you have to worry about speed on the test. Yeah. Do we need another example? Okay, well, let me think of a hard problem. Oh, the card problems. Let's do some card problems. You guys never did like card problems. Do you have card problems tonight? Yes. Okay, let's just do a couple and then we're done. Let's do poker. Everybody likes poker. Unless you don't. My wife called me yesterday. She's in Las Vegas. She said she won $1,000. Like poker. Whatever that means. Okay. We're gonna randomly deal a 5-card hand. Okay, from a standard deck of cards. No wild cards. What's the probability of getting? Okay, what do you want to do? Royal flush, two of a kind, 2 pair. What? Pick one. 2 pairs. Make up your mind. I'll do whatever. 1 pair. That's the hardest one. Okay, 1 pair. Let's do 2 pairs. Why do I even ask you? Because I don't even listen to you. 2 pairs. Now, you guys understand what 2 pairs are? That's like 2 jacks and 2 sevens. 2 queens and 2 eights. Is this, what if you get 4 sevens? Is that 2 pairs?
No.
Yeah, but look, it's 2 pairs. No, if you count, no, that's 4 of a kind. Okay. Okay, what's the probability of, so, the denominator is going to be, if you have 52 cards, how many ways can you just pick 5 of them? 52, choose 5. And remember I told you that number is 2,598,960. No, okay, never mind. Okay, now, what about the numerator? Now, see, the only difference between this chapter and last chapter, we just figured out the numerator part. All we're doing now is adding the denominator to it. Come on. Okay, 2 pairs. Do a specific case. How about 2 jacks and 2 sevens? And then the 5th card cannot be a jack or a 7. Okay, so how many jacks are there in the deck?
4.
How many ways can you pick 2 of them?
4.
And what about the sevens? Okay, and then how many cards in the deck are not jacks or sevens? 44. How many ways can I pick 1 of them? Okay, so this would be the probability of getting 2 jacks and 2 sevens. But then there's other cases, right? What about queens and eights? Or aces and fives? So what is the multiplication factor? 13, choose 2. Again, you know when you do card problems, I tell you, just write this out. It helps a lot, you know. There's 13 of these. How many ways can I pick 2 of them to be this and that? Jack and 7, queen and 4, 9 and 2, ace and 5, 13, choose 2. There's your answer. Now you gotta simplify it. But you don't have to worry, I guarantee you the answer is less than 1. No answer will be bigger than 1 on the test. You don't have to worry. Okay, you want to compute this for funsies then? What if you had this on the test? We'll just leave it. Take the -1. Come on, this is not that hard. Okay, look, 4 choose 2, go. 4 choose 2 is 4 times 3 over 2 times 1. Times 6 times 44 times, what is 13 choose 2? 13 times 12 over 2. So 13 times, just leave it 13 times 6. You know why? Because we'll let the canceling begin. On the bottom, 52 times 51 times 50 times 49 times 48, all over 5, 4, 3, 2, 1, but that's going to go to the top. 5, 4, 3, 2, 1, right? When you divide by a fraction, that's like multiplying by the reciprocal. And then now, let the canceling begin. And you guys know card problems, 13 is always good because 13 goes into this 4, but 4 cancels that 4. What else can I do? 5 times 2 is 10. 10 goes into that 5 times. What? What do you want to go? 4 goes into this 11, but 4 goes into that 12. 6 goes into 12, 2. But 2 goes into 6, 3. 3 goes into 51 17 times. Is that it? Yep, that's it. So all you have then is 6 times 11 times 3. 18 times 11, that's easy, 198, right? It's easy to, it's coming going, what? 18 times, see, what's the trick to multiplying by 11? Just think of it as 10 plus 1, 180 plus 18, boom. I don't know what you're saying. And the bottom, all that's left is 17 times 5 times 49, so that's 85 times 49. Come on! You want to think of that as 50 minus 1? No. So 5 carry 4, 0 carry 2. We've got 5, 6, 1, 4, 4, 1, 6, 5. The ones cancel out, so you just get 98 over 465. Yeah, some of you are actually writing that down. That's the answer. I think I'll just take the minus 1. I told you the answer is less than 1. You don't have to worry. Okay. After tonight's homework, then the fun begins. This is just the introductory part. This is what you should have learned last year. Yeah.
You gotta order your tool.
Yeah.
Oh, that's a tool.
Order tool.
Order tool.
Then I get 5 hammers and a screwdriver. What? Why would I order tool? Order a tool?